Okay, so now I should start the streaming. Okay, I left off with this sound location, so it's like 10:22. So let's try to at least finish section 2. Right. So operation log. The operation log contains a historical record of critical metadata changes. It is central to GFS. Not only is it the only persistent record of metadata, but it also serves as a logical timeline that defines the order of concurrent operation. Okay, so back to my code here. This is the only stored location. So this is not stored. Um, these two are not stored. This is these two are stored. This stored. Yup. Okay. Files and chunks as their versions. We haven't talked about versioning yet, but are all uniquely and eternally identified by the logical time at which they were created. So it's okay. Identified. So it should be like some sort of combination of unique ID slash time zone, like time epoch time or something. Since the operation lock is critical, we must store it reliably and not make changes visible to client until metadata changes are made persistent. Wait a minute, so metadata is in the memory, so it's first locked into this log operation and then updated to the metadata, right? Otherwise we effectively lose the whole file system or recent client operation, even if the chunk themselves survive. Okay, so even if it is written to the chunk file, wait a second. Wait a second. If right, okay, I think it's going to be discussed later on the chapter, but I just want to think if the writes go through not going through the client, the master, but instead it's like a client asks which chunk it should write that file to, and then it writes to the chunk directly in the chunk. And then how do the master know whether the files have been written properly to the chunk server? That's a question. Actually, yeah, that's critical question. Yeah, because the writes out the write, it just not goes through this master. So yeah, that's a question on itself. Okay, I think that's the important point that this part trying to make. Therefore, we replicate it on multiple remote machines. Who is we? Is it who are we? Who are we? Is it the so who is this? Is it the client or the master, or why is it we? I think it's only the client that replicated, or the chunk servers. I don't know. It on multiple remote machines. How do I okay, anyway, it is on a memory machine and respond to client operation only after flossing the corresponding lock report to this both locally and remotely. Okay. I need to learn more about the interaction because like it didn't make sense. Because none of this, like the master or the child server is actually the one that write the file. They are write goes through what happens from the client side. So even if it's flushing the metadata, then like if the file write from the client side is not properly flushed some way, then like what's the point? Okay, the master batches several log records together before flossing, thereby reducing the impact of flossing and repercussion on overall system throughput. So probably something like SSM. Okay, the master recovers its file system state by replying the operation log. Alright, so sorry, so this one. Local log is clear state as clear slate. And then like the master could be like on some the master could be restarted, replaced. I assume that's be true. So the local log could be like gone, and the master replicas is the source of truth. All right. So to me, must sort out that we must keep the log small. The master checkpoints its state whenever the log grows beyond a certain size, so that it can recover by loading the latest checkpoint from local disk and applying only the limited record after that. Okay, that's like definitely just write a log. The checkpoint is in a compact B3-like form that can be directly mapped into memory. B3 is on this stuff, and then well, you can technically serialize B3 and like store it somewhere. I was thinking it is like nah. It was like yeah, the in-memory representation of the checkpoint, right? I don't know. Actually, I was thinking checkpoint is more like I think B3 could be checkpoint. Yeah, I mean like it's just key file store. B3 is just short of key file store. Yep. Can be directly mapped to memory and used for namespace lookup without extra parsing. I have no idea what is namespace in this context. This further speed up recovery and improves network availability. What is improving availability? The checkpoint. You mean like because it's faster? Yeah, because speed up recovery, like once it's recovered, then it can start surfing, which vastly improving availability. I really will remove this part. But yeah, because the checkpoint can take a while. Hey, the master internal state is structured in such a way that a new checkpoint can be created without delaying incoming rotation. So wait, is it like what's it called? Like copy? No, copy and writes? Maybe it's copy and write, but I don't know how. No, I don't think it's copy and write. I was thinking like maybe the changes, the incoming mutation are going to be staged somewhere, and then the checkpoint is done in the main and then maybe later there could be like a reconciliation between that copy and the main checkpoint. But I don't know, just an assumption. The master switches to a new log file, okay, and creates the new checkpoint rule in the spread thread. What happened to the old one? The new checkpoint includes all mutation before the switch. Okay, it can get created in a minute or so for a cluster with a few million files. When completed, it is written to disk, both locally and remotely. Wait a minute. Recovery needs only the latest complete checkpoint. Yeah, I actually know, like, I understand how, like, generally how it works, but like the details, like the implementation, I am not sure. This is very common, like the common model for like write-ahead locks. But yeah, let's just skip this part. I mean, like, let's just keep trying to model this part onto my Python code. Recovery needs only the latest complete checkpoint and subsequent log file. Subsequent means that the log file that is that are written after, sorry, the operation log that are written after the last checkpoint. That's what subsequent log files mean. Okay, so like for example, that you have 10 logs. Okay, you are about to create the 11, like it's the next operation. Like probably from that point of checkpoint. Okay, let's create a checkpoint on the 10th operation, and then like just create new one, like just create new file, and we compact this entire 10 operation into like single few checkpoint. I don't know what checkpoint looks like. Is it like I don't know, a list of operation, like each operation is new probably, but like I don't know how, because because like of a checkpoint is basically another log, like unless people no unless there are a lot of updates to given record, to given row, to given file. There's a lot of update, and like this checkpoint is going to be like collapse every update to a single file. But if the most of the use case is like a pen only, then like this checkpoint is basically like the latest state of that file. So yeah, I mean like yeah, that's basically that's what I'm thinking. All right, so consistency model. Oh wait, so okay, there's more. The current is on the latest complete string and subsequent log file. Okay, all the checkpoints and log files can be freely deleted, so we keep a few around to correct against catastrophes. A failure during checkpointing does not affect correctness because recovery could take and skip incomplete checkpoints. So there could be like, I don't know, what's it called? I forgot. The checksum thing. Solomon reads, yeah, or CLC or anything actually. So the next point, consistency model. Let's try to read it through first and like see if we can like, if it's like heavy and implementing detail, or it's just like and leaving the highly varsity picture. GFS has a relaxed, consistent model that supports our highly distributed application well, but remains relatively simple and efficient to implement. Yeah, it is like, it's relatively simple. Yeah, I mean like, judging from this, my current code, it's like not much of that complicated. We now discuss GFS's guarantee that and what they mean to applications. We also highlight how GFS maintains these guarantees, but leave the details to other parts of the paper. Okay, first, I wish I could zoom in and like, because my head should be around here, so it's not going to be feasible. Alright, so file namespace. File namespace mutation, aka, for example, file creations are atomic. Okay, what does it mean by atomic? They are handled exclusively by master. Okay, so atomic, exclusive by master. Namespace locking guarantees, namespace locking guarantee atomicity and correctness. What is namespace again? What is namespace? What is namespace again? So it's like in one namespace there are only like one thing you can create, but what is namespace? The master operation log defines the global total order of these operations. So you cannot create the same file at the same time. But what is, how does it know? I don't think it knows like the file content or something. Even the file name is the same, probably just going to reject the other one. The state of a file region after data mutation. What is file region? The mutation depends on the type of mutation, whether it succeeds or fails, and whether there are possible mutations. Table 1. Which one is table 1? Summarize the result. A file region is consistent if all clients will always see the same data regardless of which replica they read from. Oh, sorry. I was drinking my kombucha. A region is defined after a file data mutation. If it is consistent, and client will see that mutation writes in its entirety. When a mutation succeeds without interference from concurrent writers, the affected region is defined and by implication consistent. I don't understand. When a mutation succeeds, okay, without interference from its affected region. Okay, a file region is consistent. Okay, wait, a region is defined. What is region? Sorry, what is region? It's defined after a file data mutation. If it is consistent, and client will see that mutation writes in its entirety. When a mutation succeeds without interference from concurrency writer, the affected region is defined and by implication consistent. All client will always see that mutation has written. Concurrent successful mutation leave the region undefined but consistent. All clients see the same data, but it may not reflect what any of one mutation has written. Okay, this is the tricky parts that I need to understand. Typically, it consists of mingled fragments from multiple mutations. A failed mutation makes the region inconsistent. It's also undefined. Different client may see different data at different times. Which below or application can distinguish defined region from undefined. Okay. Serial success is easy. Record appended define interspersed with inconsistent. Concurrent success consistent but undefined. Sorry, what is undefined? defined after a file determination. If it is consistent and client will see that mutation applied in its entirety. Okay, this is defined. I mean, it's consistent. When a mutation succeeds without interference from concurrent writer, the effect region is defined. File region. So it is like file region. It's just like it's not an entire file. It's just like subset of the file. So it could be like cross section, like of multiple chunks. Concurrent successful mutation leaves the region undefined but consistent. Okay, so what do you mean by that is this? Okay, undefined is that the data could be garbage, but every client will see the same garbage, right? But it typically may not reflect what any one mutation has written. Yeah, so that's that's what it means. It is garbage data. It's undefined, but yeah, everyone sees the same garbage. Is that what it means? Why is it complicated? Typically, it consists of mingled fragment from multiple mutation. Yeah, mingled fragment means that it's garbage data. Okay, why so complicated, man? It is consistently wait, cons aka garbage data. How to make it smaller? How to make it smaller? Size. Yeah, I get garbage data. A failed mutation makes the region inconsistent, hence also undefined. Different client may see different data at different times. Right, so that's equally garbage, but different garbage per different client. Okay, why so complicated? We describe below how our application can distinguish different region and undefined region. The application do not need to further distinguish between different kind of undefined region because that's garbage data anyway, so you don't have to even attempt to read that. Data mutation may be writes or record events. A write causes data to be written at an application specified file offset. Application specified offset. Okay. Record append causes data. The record to be appended atomically at least once, even in the presence of concurrent mutation but at an offset of GFS choosing. In contrast, a regular append is a merely write at an offset that client believes to be the current end of file. Okay, this is interesting. Because of the record to be appended atomically. At least once, even in the presence of concurrent mutation. Carpet. Okay, so where am I? Oh, record append access vector to be appended atomically as once. Press of concretion, but at an offset that is choosing. Let me think. But in contrast, regular. What was it? Well, sorry. What is the difference between regular and non-regular? In contrast, regular append. Sorry, what is the other one? Right is it's like random specific. It's random right. Okay. A record append causes data to be appended atomically at least once in the presence of concurrent mutation. Oh, okay. But at the effect of choosing. So when you are controlling write to something, then like GFS will choose. Okay, you write at which offsets, and the other one you write at which offset. GFS choosing, right? And in contrast, ritual append basically like non-concurrent writes. I mean, like, so at the offset of choosing, does it mean that the file could branch out? Wait, sorry. So, concurrent successful mutation leave the data undefined. So basically, this is what it means. All clients same data. Like, okay, that's GFS could like randomly choose different offset for you. Right, this is could probably because client has no like, so two clients can write to the same file offset, right? Because basically they have no idea who is writing to this file, because it's not being gated by the master node, which is quite makes sense. But like for example, the child server could actually prevent that. You know, why don't the child server prevent that? Child server prevents the any attempt to do this stupid concurrent write. Okay, anyway, the offset. Wait. The offset is returned to the client. Wait. And mark the P of the defined region that contains the record. Wait. So who is going to write this part? The offset is returned to the client. Wait. The offset is defined return to the client. What does it mean? It's returned to the client. It's like the function return, but I thought that this is, so this information like the defined region is on the client, because the client is the one who writes the data. So it's returned by the client itself, right, from the child server. In addition, GFS may insert padding or record duplicates in between. Why? Why record duplicates, man? They occupy regions considered to be inconsistent and are typically dwarfed by the amount of user data. The occupied region considered to be consistent. After sequence of mutation, the mutated file region is guaranteed to be defined when not garbage. Okay. and contain data written by the last mutation. GFS achieved this by applying mutation to a chunk in the same order on all of its replicas. How do you define the same order if it is client things? I mean, who's going to preserve this orderness of this? Because your master basically it's not doing anything. Like how would you define that? Like if say that okay, the client gets this list of something, right? So file channel is one. Okay, I have to, okay from this is your master, and like master is thinking okay, this is the list of channels where you have to write from, and you have to write to, and just use this whatever you want, and that's why I'm thinking man, it's not this page. Where's that? Okay, so that's what I'm thinking, like how would you might apply that replica? I see. Does it mean that every time you receive this and you write that to some channel server, okay, it's not being replicated yet? Blah blah blah. I'm sorry, I'm quite sleepy, but blah blah blah. Open causes blah blah blah. Okay, where am I? After sequence of segmentations, file regions going to be defined in content server by written by last mutation. Yeah, okay, this one. Applying chunk in the same order. So who's going to do this? Oh, it's replica. Yeah. And using chunk version numbers to detect any replica that has become stale. Chunk version. Okay, so chunk version. Chunk server. Still because mismutation. Well, it's down, server is down. The replica will never be involved in a mutation or given to client asking for asking the master for chunk location. But in the same way, how let's just continue. Since client has chunk location, they may read from still replica before the information refresh. Yeah, so I was thinking like, what is a refresh rate? Like, what if just at the same time bunch of bunch of replicas just like go just blow up or something, then how would you they may read from the replica before the information is refreshed. Yep. So there is limit by the cache entry timeout and the next open of the file, which purges this from the cache all chunk information of that file. Moreover, as all files are can only save replica user returns the primitive to the end of chunk rather than update data. When your reader tries to end contact manager, it will immediately get the current chunk location. I'm gonna skip this part. No, skip it, like continue tomorrow. Okay, I think it's like 11 p.m. so let's stop this stream now. Yep, thanks so much for listening to my garble.